the Women in STEM Society. So I'm here to tell you about an upcoming talk we have next Tuesday called Understanding Gender Diversity Challenges in STEM. So this is going to be an interesting talk given by Claudia Sabo, who's the Associate Dean of Diversity and Inclusion. And it's going to be an overview of gender diversity challenges at all education levels, and also a discussion on things we can do and successful initiatives to encourage more women into STEM. So there's going to be free pizza. It's going to be at 2 o'clock next Tuesday in Bar Smith 534 with pizza at 3 o'clock in the mezzanine. Please come along. Everyone's welcome, men, women, whoever, if you want to learn more about diversity in STEM. I think it's really applicable to all of you, because if you look around the room, there's a serious gender imbalance. So come along, learn more about initiatives we can do, and that's all. Thank you very much.
Okay, thank you. All right, so actually, Amali sent me an email yesterday evening telling me that she doesn't feel well, so that's why I'm subbing for her today. Today, we are going to talk about memory. So first of all, we'll spend like 5 to 10 minutes talking about the computer architecture, the different type of storage spaces in a computer, and then we will talk about specifically memory for C++. So how does C++ organize memory? And I'll also take this opportunity, I think this is a very good opportunity to talk about how to debug C++ program as well. So I will mention the GDB debugging tool for C++ program. The reason I want to sort of like also talk about GDB today is that what is the whole purpose of a debugging tool? Well, a debugging tool, for the most part, allow you to conveniently access what's going on inside the memory at this moment. For example, when your program crashes, what's happening inside the memory? The state of you want to analyze the state of your program, right? So because we are talking about memory today, might as well just like show you how to use tools to analyze the actual tools to analyze memory. Okay, so that's the plan today. And first of all, let's talk a little bit about the computer architecture. So there are actually 3 types of storage space in a computer, and I'll just list them here. Okay, so we have this is too small. Let me just enlarge the font size a little bit. Arial Black, 22. Okay. So we have hard drive, right? That's basically one type of storage space, and we also have memory. And there's actually a third category, which is CPU cache. All right. So now we have this. So for modern day computers, for a laptop, the desktop you are using, we have these 3 main categories of storage space. Now let's first talk about like the difference and also let's say, the technology and the difference between these 3 types of storage space. First of all, for hard drive, let's say if we want to create hard drive. So let's say right now you need to pick, let's say you're working for a hardware company, you want to design a new computer and you want to pick the appropriate technology for hard drive. And then in order to do that, you have to think about like what hard drives are for, right? So basically for this type of storage space, what is the purpose? What is the main purpose of it? And once you figure this out, you'll be able to pick the appropriate technology. So for example, for hard drive, in my opinion, well, the main purpose is actually for storing things, right? So for storing movies, storing your picture, your programs, and everything. Now, because storage is the main purpose, and we would then kind of figure out that, well, it would be nice that if, for example, if it can be persistent in the sense that the data is always there, all right? Even if I shut down the computer, the data should be there. So that's one property I definitely need. Okay, and then I also kind of need it to be large because I need to put like Blu-ray movies, or like a lot of pictures on it, right? So I want it to be persistent, I want it to be large, and of course I want it to be as fast as possible. That's basically true for every type of, for any component in a computer. We want it to be as fast as possible, right? But then so we might as well just like skip this entry. For every component, we need it to be as fast as possible. But then we have to think about it like is speed actually something that matters the most for a hard drive? Well, it would be nice, certainly, to make it as fast as possible. But let's just say, let's say I have some photos on my hard drive. Maybe in a whole year, I'm not accessing it for even once. Maybe I'll access it like 3-4 times in a whole year. All right, so for hard drives, at least for some functionalities, of course, we may have programs that we use every day. We access them every day. But there are also some other parts where I don't access at all. I'm just using it for storage. And maybe speed is not as important as basically when it comes to other components in a computer. So speed may or may not, let's say, may not be too important. But of course, we still want it to be as fast as possible. Now, another thing is that, by the way, another good thing, so for example, when we talked about this property persistent, basically I want to ensure that even if I shut down the computer, the data is already there. Okay, so even if I have no power, the data should be still there. Now that is actually good in another sense because I'm actually able to transfer a lot of data in a very large bandwidth. So currently, for the current technology level, the fastest way to transmit large amount of data actually is not basically using the best internet architecture. The fastest way to transfer is to load all the hard drives in a truck and then drive the truck from point A to point B. All right, that would provide you the largest bandwidth. Maybe after 50 years, it's no longer the case, but right now, that is still the case. Well, if we can keep the data without power, then we can load our data onto a truck and then drive the truck from point A to point B. All right, so basically for hard drive, maybe I want to ensure that I definitely need this, okay, I definitely need this, and I definitely need this. Speed, well, okay, it would be good to have that. Okay, so that's basically hard drive. Now let's talk about the memory. Memory is basically where you load, basically your operating system would look at the program on your hard drive, and then if you're running this program right now, you would load this program into the memory. And the memory will also be used as some kind of like a scratch pad. So you have some intermediate data that you need to store. You have some resulting data that you need to store when you run the program. So all those will be inside the memory. Now for memory, okay, so do we count, for example, we don't really need it to be persistent. Okay, don't need to be persistent without power. Because, well, the main reason I use a memory is that I want to use this as some kind of like some kind of scratch pad, as I just mentioned, right? So intermediate results and basically, for example, the calculation results of your program, I would first get it in the memory, and then I would display it to you somehow. For example, in the form of some kind of like a screen output, in the form of like other I/O output, like a printing to printer or whatever. Okay, so maybe I don't need it to be persistent without power, and I don't really need it to be that large in a sense, okay, because even if I have like a movie that's huge, that has, for example, a few gigabytes of size, I don't really need to load the whole thing inside memory, because at any moment I'm only watching the next couple of seconds, right? So you only need to load a little bit inside the memory, and then you'll be able to watch the whole movie, even though it is large. Okay, so may not need it to be too large, okay? And of course, we want it to be as fast as possible, right? So speed as fast as possible, because this is basically the scratch pad, and we certainly want it to be as fast as possible. Okay, so now the third category, CPU cache. Now, what is CPU cache? CPU cache is actually a very small amount of even faster memory that is built on the CPU chip. So the CPU would actually, basically what happens is that if you have a program, first of all, you have a program. The program is on a hard drive. You run the program is loaded into the memory, okay? But then, at any moment, the CPU is only working on a small part of that program. So for example, right now, I'm just dealing with displaying the menu, okay? So I would just load, I have basically the program inside the memory. I only need to get a little bit of it, and that's highly relevant to my current task. I'll just load that into the CPU cache. And then the CPU will work on that part of data. And then now if I finish displaying the menu, I'll do something else. I will load another part from the memory into the CPU cache. Okay, so essentially what happens is that the hard drive is the largest part, and then the memory, I'm sorry, let me just draw it a little bit. Okay, so for example, you can think of it this way. The hard drive is the largest part. You have a lot of program, and you have a lot of other data, for example, like a photo, movie, or whatever. Okay, and then one program is loaded into the memory. The memory would then be slightly smaller, and but then still, this is still too much information. And at any moment, the CPU, I'll just call this memory, and then this is the hard drive, and then cache. Okay. At any moment, the CPU is only working on a small part of the program. So only those is loaded into the CPU cache, and then CPU would work on, basically this is CPU, okay? And then CPU would work on this part. Later on, I would work on, for example, this part of the program, then I would load this to the cache. Okay, so from the largest all the way to the smallest, and also from the slowest all the way to the fastest. So CPU cache also don't need to be persistent without power, okay? And don't need it to be large. And speed is very, very, very important, okay? Because your CPU is very fast. For this part, this is the part CPU directly works on, so you want this part to be as fast as possible. Okay, so we have these three different aspects. Now you may be wondering, okay, it seems like you may be thinking, okay, why do I have these three different storage space? You kind of understand that maybe it is due to cost. Well, so hard drive is cheap, so we can make it slow. This is cheap, so we can make it large, and then because it's slow, it's cheap. And then this is slightly faster, slightly more expensive. This is the most expensive. So you kind of get that, okay, from a practical point of view, I want to basically build a usable computer using a reasonable amount of money. So that's why I have these three different layers. But what if I have an unlimited amount of money? I just want to throw it out there and build the fastest possible computer. So can I actually change this architecture a little bit? So for example, you may be thinking, all right, so hard drive, the data is there without power, okay, but then it is very slow. Can I actually replace it with memory? So how about this? I will just build a computer that doesn't have hard drive. It will just have even larger memory, and then I will use memory as the hard drive. Now, of course, the one issue is that your computer needs to be turned on all the time, because once there's a power shutdown, you lose all your data, okay? So if you have unlimited money, actually that's a reasonable thing to do. Actually, there are people, researchers right now doing this kind of like a sort of like inventing this kind of new architecture. So for example, let's say I have a cloud center, I have a cloud data center. The data center, basically 99.9% of the time, I have power. So, but of course, I still need to prepare the case where I have some kind of earthquake or like a hurricane, and then if I lose power, then I lose all my data. I kind of want to avoid that, right? But in a cloud data center, what you can usually do is that you can build, for example, 3 different centers in 3 different cities. One in North Carolina, the other is Sydney, another in Frankfurt. And you have basically you have your data stored in all 3 different data centers. And you can use memory, because 99.9% of the chance you have 3 copies alive. Even if there's a hurricane, it's extremely unlikely for like basically at this moment you have like one hurricane in North Carolina, one earthquake in Frankfurt, and then one whatever in Sydney. Okay, yeah, whatever, like drawbell in Sydney, and then yeah, that's extremely unlikely. So yes, you can actually replace hard drive by memory. You just need to spend a lot of money, all right? And then now the next question is that, okay, can I actually replace memory by CPU cache? Because CPU cache is the fastest technology out there. So this is the fastest part. So can I just use this as this? I just make it larger, right? I just make it larger. Yeah, well, here are a few issues. First of all, the current technology for CPU cache has a few drawbacks. One is that it consumes a lot more power. So they both require power to be operational. This one requires a lot more power, about like 5 times more power. So it's environmentally very unfriendly, and also it costs a lot of money if you want to replace memory using this CPU cache technology. Now, another thing is that the current technology generates a lot of heat. So if it generates a lot of heat, if you use that for memory, because it's actually larger, you have a lot more caching units in that area inside your CPU, your computer case. It would generate a lot of heat. So to stop like a fire hazard, you need basically a very expensive like a thermal control system in your case as well. So let's say even if you say you don't care about money at all, you can build a huge PC case with like some kind of like a hydrogen cooling system, and then you definitely insist using this as memory. But then the thing is that even if you do it this way, you won't actually make it as fast as an actual CPU cache. The reason CPU cache is a lot more faster than memory technology is that this is actually built on the chip. Okay, so if you actually want to use this as memory, you have to increase your chip size. But then if you increase your chip size, you can fit a lot more cache memory onto your CPU chip. But the thing is that there's actually some physical, how to say, let me put it this way. Because CPU is so fast, you actually care about the distance between the physical distance between the memory and your CPU. Because basically there's the sort of like the speed of travel of like electronics between these two parts. You actually want to keep the physical distance small. Now, if you put a lot of cache like components on your CPU chip, only those that are very close to the CPU can be fast. Those that are further away, due to their physical distance, they're actually slower. Okay, so that's why even if you have unlimited amount of money, you want to basically use this for actual memory, you actually won't be able to reach the kind of speed that you need. So it's actually economically much more reasonable to still do it this way, and then because at any moment your CPU is only accessing a small part of memory anyway, so you actually increasing the size won't actually give you the performance boost that you are hoping for. Okay, so that's basically some architecture discussion on the storage space in a computer. Now let's move on to what we actually care about in this course. That is how C++ organize memory. Okay, so now let's talk about how C++ organize memory. Let's say, actually I shouldn't close this document. Let's say you are designing a C++ compiler yourself. Let's say right now someone has designed C++, but it's just a design on paper. All right? So we have this language specification on a piece of paper. We want to turn that, sort of like implement that on a computer. Basically, I want to create a program that understands C++ code, and then either interpret it or like compile it to machine code. Okay, so, and then in order to write this kind of program, you kind of need to figure out like how should I organize memory for a C++ program. First of all, let's first talk about like in a C++ program, where do we need memory? All right, so what kind of like storage we actually need for a C++ program? Of course, we need to, the operating system needs to load the actual program into the memory, but that's the not so interesting part. We don't care about that. Let's just talk about like the actual memory usage you will ever need. So in a C++ program, we have different type of variables. Let's just list a lot of them, and then think about like if we are actually designing the compiler ourselves, how would we organize the memory? So for example, in a C++, I have global variable, okay? So for example, I have like a global integer variable, I have a global character variable, I may even have like a global, for example, some kind of like a integer array, okay? So basically, I have global variables. It's kind of pointless to list them all, but we have global variables, and then we also have, for example, local variables. I may have some kind of like a local variable, I'll just call it a local variable inside the main function. Local variable inside the main function, maybe the type is int. Maybe some kind of local variable inside the main function where the type is double or whatever. Okay, so we have global variables, we have local variables, and then what else? So can anyone tell me like what else? What kind of like other, huh? Yes, indeed. We have private variable that's inside a class, but then technically that's part of an object. So basically when you create an object, you would also create a memory space for all the variables. Now it really depends on where you put the object. You can have like a global object, you can have a local object, you can have object in a function, etc. So that kind of falls into either the global category or the local category. So we actually have something else. Calculation? You mean the actual program? Yeah. That's basically the operating system would load that part, and then we wouldn't touch that part anymore. So that's the easy part. For now, let's don't talk about that part. Okay. So, Function inside the main, separate function. Yeah. So we have like other functions. So for example, we have some other function, some kind of like a function, and inside it we may have like a local variable. And then another thing is that we may also have like some kind of like a parameter. So for example, for a function, let's say my function is defined this way. That is int foo and then double x. So let's say I have a function like this. So and then inside, for example, I have like a int a and whatever. So inside this function, I have int a, and then there's actually another part. We also have the parameter. So I need somewhere to store the parameter value. So maybe I can just like put down like a local foo and a parameter and maybe type double and a name x, whatever. Okay, so, and we have this. Now we actually have something else as well. By the way, For example, let's say you have a function, you want to maintain a counter. You want to maintain a counter on how many times you have called this function. And how would you implement that? Maybe you can put the counter inside the function. So how would you do that in C++? Yeah, but you want to keep track of the counter. Let's say you want to keep track of the counter inside the function. The counter is actually stored inside the function. How would you do that in C++? Yes, exactly. Thank you. We have like a static, some kind of like static variable. Because, for example, like inside the foo, in order to count how many times I call a certain function, basically what I can do is that, for example, like a static int counter, and then initially it's 0, and then every time I call this function, just increase the counter. And then I'll be able to basically get the number of times I'm calling this function. So we have like a static variable as well. So basically static variable, some type, for example, int or object or whatever, like an object or character or double, whatever. Okay, so at the end of the day, we have global variables. We have local variables inside main. We have local variables inside functions. We have function parameters. Those are also the kind of information that I would actually need to store. So I need to create a memory space for that. And then I also have static variables inside the functions. Okay, so I have all these types of variables in C++. This is actually not the complete list. I have a lot more. For example, sometimes I can do something like this. For example, int a, some kind of array, and then this array is that I'm going to create an integer array of size 100. That would be another kind of like a storage space I would need. So I need you, here I'm allocating enough space for 100 integers. So you would have this kind of like a dynamic request. Or it could be, for example, let's say some kind of like a double, and then D, and then new, for example, double, for whatever, just like a, okay. So basically you can also make dynamic request. So these are some other parts where you would need to figure out how to manage the memory space. All right, so basically here I've listed all the different types of variables and also different ways to sort of like declare them. Sometimes just like using static, sometimes using dynamic allocation. Now let's see how we can actually organize this memory. First of all, the easy part. The easy part is the global variables, something like this. These are easy because, for example, I have a global variable, int, some kind of like a, for example, int year equals 2018, all right? So let's say I have a variable like this. In C++, a global variable can be accessed throughout the program. So when I start the program, this value 2018 should be there. When I end the program, this value should be there. Throughout, the value should be there. I don't need to like switch it in and out. Of course, maybe I kind of want to do that if I want to like save memory space, but that seems very inconvenient. So the easiest way to deal with things is that, okay, if I needed this value, this integer value 2018, to be inside the memory throughout the life cycle of my program, so might as well just do it this way. When I start a C++ program, I figure out how many global variables are there, calculate how many bytes I would need for those variables, and then just allocate all of them in the beginning, and then deallocate all of them at the very end, and then don't touch them at all throughout the process. I don't need to deallocate them or reallocate them during the running of my program. So global variables are actually easy to deal with. I can just create a section inside memory that's just for global variable. And the size of that section can be calculated based on the actual C++ code. I'll just scan through the code. It's a text document, right? I'll scan through the code. Whenever I see global integer variable, I figure that, okay, I need 4 bytes for that. And then I see a global character variable, I need 1 byte for that. So if I only see these 2 global variables, that means I need 5 bytes for the global variable section inside memory. I'll just allocate that 5 bytes, and then that's it. All the global variables are taken care of. So global variables are the easy part. All right, so these are the easy part. These are the easy part. Just allocate a special area for them, and then that's it. Now, let's talk about whether we have some other easy part. Actually, these are also the easy part as well. Static variables are also the easy part. Why? Because static variables, I need those storage space throughout the life cycle of the program. Because whether I'm using this function or even if this static variable is defined inside a function or inside a class, whether I'm using it or not, that value needs to be there later on. So right now, even if I'm not using it later on, when I access it, the value needs to be still there. So maybe what you can do is that when you are not accessing it, you kind of like write it onto the hard drive, and later on when you need to access it, you load it from the hard drive, but that's very inconvenient and very slow. The easiest way is just to keep it inside the memory. So if you have a static variable, just keep it inside the memory. When you start a program, load it into the memory, and throughout the whole program, just keep it inside there, and then only allocate it at the very end. So essentially, the static variable is just the same as the global variable. Okay, it's just the same. You would scan through the C++ source code, the text document, figure out like how many global variables are there, how many static variables are there, and then calculate how many bytes in total I would need these 2 types. I would need for these 2 types of variables, and just allocate a large enough special section for both global variables and static variables, because those values need to be inside the memory throughout the program. All right. So these 2 are the easy part. And then we also have like a local variables inside the main function and the local variables inside the other functions. Now they seem to be different. First of all, local variables inside the main function, I kind of need that throughout the life cycle of the program. Right? So basically inside the main function, because at any moment, basically, at any moment of your program, you are inside a certain function. That function is either the main function itself, or that function is called directly or indirectly by the main function. So the main function is always alive throughout the program. Right? So for example, let's say your main function calls function f. Function f calls function g. And then at any moment, you could be either in main or in f or in g. But the main function is always there. Even if you are in F, later on you need to return to main. Even if you're in G, you need to return to F. F will then return to main. So the main function should always be there. So maybe what you can do is that, okay, the variables inside the main should be there. I can just treat it as part of just like global variables, just like static variables. You can just scan the main function, initially calculate how many bytes you will need, and then create a special section for that. Well, that's actually one way to organize things. That's not actually a bad idea, but that's not how C++ organizes things. Well, what's the reason? Well, the reason is that actually C++ has a much nicer systematic way to organize the variables we will need for a function. So for example, you have a main function, and then inside this main function, I would first call the function g, and then call function f. And then what is my function f? Function f simply calls function g. And then what is function g? Function g basically does something. Okay, it doesn't call any function. All right, so basically, initially I'm inside the main function, and then I'm calling function g. But the main function should still, the relevant information should still be kept inside memory, because later on I need to return to the main function and then continue where I left off. All right, so the main function should still be in the memory. And then now I also need to load all the information for G inside the memory. Okay? And then once I finish this, I no longer need those variables. For example, I'll just call it int, for example, like ng.
number in function g. Okay. When I'm running this function, I kind of need this to be inside the memory. But when I finish it, I don't need it anymore. So basically, when I'm here, okay, let's say inside the main, I'll just create like an n main, okay, and not basically some kind of like a local variable. And here inside f, I'll just call int nf, okay, ugly, but whatever, okay. So when I start my C++ program, this should be inside memory because I'm using the main function. Throughout, I may need to use it. Then I'm accessing G. This should still be inside memory, but then I also need to load this into the memory. But after I finish G, I don't need it anymore. Throw it out, okay? I don't need it anymore. When I reach this point, I don't need ng anymore. Then I would load F. Inside F, I need to load this into the memory. I still need to keep this in the memory. I need load nf into the memory. Then I'm running G. This time, I need to load ng into the memory. And then after I finish F, I no longer need ng in the memory. I still need nf in the memory. After I finish F, I no longer need nf in the memory. I still need the main in the memory until I finish the whole thing. That's when the program stops. Then I don't need anything inside the memory. So basically, we have this kind of like a workflow. And then there's one very easy way, one very nice, elegant, and systematic way to organize the memory. We can do it this way. Basically, let's say this is your memory. This is your memory, all right? Just to remind you, we have the main function. Okay. Okay, I'll just put it this way. Okay, this is our original program. Let's say this is a memory. I'll just use it from the top all the way to the bottom, or from the bottom all the way to the top. It doesn't really matter. Let's just say the operating system gives me this much space for me to use. This is just my scratch paper. I can use it however I want. I can start from the middle, but why do you want to do that? Okay, I just start from the top. So I need to load the main function inside the memory. That would be, I need n main inside the memory. And maybe I also need some other bookkeeping information for the main function in this part as well. Okay, so basically I will allocate one part for the main. And then when I reach this part, I need to keep this inside memory, but then load G. So what I can do is that the natural thing to do is that, okay, I need to load G. Just load G. Load G into the memory, right? So it's very natural because this part is unused. I need to load G, just load it. That's the most natural thing to do. After I finish G, I no longer need this part. So this is deallocated. The free area is once again this. Then I'm accessing F. I need to load what's about F inside the memory. So the most natural thing to do, once again, is just to load, for example, let's say F uses this much. This much space. I'll just load F inside memory, all right? So just load F, and then I need to call G. But then this time, this is still needed. This is still needed because I'm still inside F. And then I need to create, basically allocate space for G. The most natural thing to do is just use the unused area, and then just like load G. And then once I finish this is gone, okay? Deallocated. Deallocated. This is once again the free space inside memory. Right now I have main function, then F function. And then I finish F, this area is no longer needed, so it's gone. And then this is the free space, this is the main function. Then I finish the main function, I no longer need this part. This is gone. And then that's when I stop the whole program. I deallocated all the memory, I stopped the whole program. So essentially what happens is that you just do the very simple thing. That is, whenever you need to load a memory, whenever you need to load a function, use what's available from the top. And then whenever you stop a function, just remove it from the memory space. And then that's it. Okay. And then if you do it this way, it turns out that you have an order. The order is basically called first in, last out. So in the beginning, you only have main. Later on, in the second step, you have main. then you have main, then function g. So the second step, main, then function g. And then later on, g is no longer used. You have main only. And then later on, you call f. So main, then f. Then later on, inside f, you are calling g. So main, f, and then g. And then you finish g, you have main, f, and then no longer g. And then you finish f, you have just the main. And then you finish everything, you have nothing. That's when you stop your program. So basically, we have a very systematic, elegant order to do things. Whenever you load a function, just load it in the, basically, using the rest of the available memory. And when you remove it, you just remove it. And then you have the first in, last out order. The main function is the first one you entered, and then it is also the last one that is removed. And then here, function f is added before g, then it is removed after g. So first add f, add g, remove g, remove f. So first in, last out, last in, first out. That's basically the order, if you use this very natural way to organize the memory needs in C++ program. All right, so this is actually called the stack data structure. First in, last out, last in, first out. You can just imagine you have a stack of books. You have a stack of books. You put one book on the desk. You put another book on top of it. You put another book then on top of it. When you remove things, the last thing you added into the list is the first thing you move out. And then this is the second last thing you add. That's the second last thing you move out. And then this is the first thing you added. That will be the last thing you move out. All right? So basically, for local variables in C++, we can easily organize it using this first in, last in, first out idea. Okay, so that's basically Basically, I have this very elegant way to organize all the local variables. What? All right, so now finally, I also have something like this. This is something I haven't taken care of. Well, it turns out that this is the difficult part. This difficult part because let's say, first of all, I collect a user input. How many integers do you need to deal with in your program? If a user inputs 100, then we'll allocate 100 integers. If a user inputs 1,000, I would allocate 1,000 integers. So here, sometimes I have dynamic memory needs. It depends on the user input. For example, you are running a web service. And then at this moment, if there are 100 users, 100 concurrent users, you need 100 memory sections for each of them. If there are 1,000 users, you need 1,000 individual memory sections for that. All right, so basically, when you have dynamic function needs, it gets a lot more difficult, okay? You actually cannot figure out any systematic way to organize them. So what you can do is then, basically, once again, do the most natural thing. The most natural thing is like this. This is my memory section, all right? So I've already some for example, I already have some main function. I've already some like a function f and then function g. And but basically, let's say the current status is like this. And then I have some dynamic needs. I need to the user tells me right now he needs 100 integers. I need to find space for 100 integers. So what I can do right now is that, okay, so how about this? I'll just find enough space inside here. That's large enough for 100 integers. So if I use this part, that kind of messed up with my algorithm. Because later on, for example, if g calls another function I naturally, for example, if G equals H, I naturally want to put it this way, right? So basically, the upper part, those are the part you kind of don't want to touch because it would mess up with your elegant stack, first in, first out, last in, last out, last in, first out algorithm. So maybe what you can do is that, okay, I'll just from the bottom, from the other direction. There's really no top and bottom. You can just think of one direction and the other direction. So maybe what I can do is that I'll just search from this part, from the bottom up, and then find to see whether I can find enough space for 100 integers. And then I'll just put it there, all right? And then later on, for example, the user asked me to find get space for 200 characters. And then I'll just put it here. Now let's say the user tells me I no longer need that 100 integers. Then what happens is that, okay, so the earlier parts are still maintained using the elegant stack algorithm. But then if the user tells me that he no longer needs that 100 integer, currently my memory is now like this. Now, if the user tells me, okay, now I need 50 integers. What I can do is then I will still search from this area, and then I see, okay, nice. I can fit 50 integers inside here. All right? So, okay, you have a question?
Is there a pre-allocated space for that area, or is it created when you create variables?
What do you mean?
So, like, would there be a set amount of memory for the 200 characters and 100 integers already, or when you write those variables, sort of allocate to them?
Basically, for example, are you talking about if I'm allocating 200 characters, is there a specific amount of space I would need for that?
Yeah, is the space already there?
No. You basically calculate based on the user input. If the user tells me I want X characters, then I figure, okay, every character needs 1 byte. You need X characters, that altogether I need X bytes. So basically, you would just go from this area and search until you have enough space for X bytes. And then you create that. Basically, reserve that part. Okay. So for example, now let's say user tells me he no longer needs these 100 integers. Later on, the user tells me he needs 50 integers. Okay, I can put it here. But then if the user tells me then he wants 60 integers, then I kind of cannot use this part. I have to use this part, 60 integers. And then later on, if the user tells me that he needs 30 integers, then maybe I can put it here. But if the user once again asks for 61 integers, then I cannot put it here. I have to put it in this part as well. So basically, here, when it comes to a dynamic allocation, it gets a lot more messy. So you kind of need to search until you find a place, and then you put your need there. And then eventually, over time, you would create a lot of gaps inside your memory. These are the kind of gap that you cannot, it's very inconvenient for you to reuse. For example, now let's say the user asks for another 45 integers. And then I'll give him that. Now I have at least this tiny gap, which is worth 5 integers, which is 20 bytes. 20 bytes. This is very difficult for me to use anymore for the rest of my program, unless I have some request that's actually smaller than this. But if that's unlikely to happen, then this is actually wasted memory. So, all right, so basically, when it comes to dynamic allocation, it's a lot more difficult, and then we actually need to basically design some kind of a scheduling algorithm in order to more efficiently organize those dynamic needs. For example, what you can do is that you can search from the bottom, and then as long as you find a block that is large enough, you put your request there. Or what you can do is that you search all the way, you find the most appropriate block, and then put your newly requested area there. For example, if the user is asking for 50 integers, you find a block that has the size of 55.